Today we have Maruša Bradač from University of Ljubljana. Maruša did her PhD at University of Bonn at the Max Planck, and then did a postdoc at Stanford, and then a Hubble fellowship at UC Santa Barbara, and then moved to within California to professor at UC Davis, and now is at University of Ljubljana. She's also a member of the NIRIS GTO team, and today she will be talking to us about star formation in the early universe under the microscope with gravitational lensing. Please.
Thank you very much. Thank you for the kind invitation. The last time, actually the only time I was in Cambridge was more than 20 years ago. So a lot has changed and I'm super excited to be here. I'm also super excited about all the interactions we were already having. There was some really good discussion this morning. I'm apologizing if I maybe sound a little bit tired. There was an important deadline for a lot of us yesterday. I also don't blame if anybody falls asleep. But I'll try to show you some exciting results so you don't fall asleep. So I'm going to be telling you a lot about how we use gravitational lensing to study the earliest galaxies in the universe. In particular, we're interested to know more about the Epoch of Reionisation. So this is the classic timeline that is made by NASA. So we're studying from the Big Bang. On this info slide, it says 14 million years, first stars form, later first stars form. I think this needs to be a little bit revised because we are seeing stars forming earlier and earlier. But it's really the Epoch of Reionisation that these first stars and galaxies are influencing. So we are having a lot of neutral hydrogen in the early universe, and those first galaxies and AGN are the sources of reionization which actually helped reionize hydrogen to end the Epoch of Reionisation. We are doing this with JWST, and JWST really is a new chapter in astronomy, because when we are talking, what I'm showing here are the spectra of galaxies and AGN, and basically at high redshifts that we are interested in at redshift above 7, what we had access to with Hubble was only the young stars. So you can see here the stellar continuum spectrum in blue and the nebular emission in what's that color, cyan. And basically, we were only having access to the rest frame ultraviolet light to really study these early epochs. But now with JWST, what we get access to is also old stars and all the emission lines that we really can use to study the physics of these early galaxies. So we do this. We send Webb into space, and what happens is it serves us a lot of surprises, which made me incredibly happy, because my biggest fear is we would send Webb, JWST up, and all we are going to see is the same things we already kind of thought is going to happen. But luckily, this was not the case. So when preparing this talk, I was thinking, okay, let's sort of get a broad overview of what is happening. So, you know, as any good student, you would turn to ChatGPT and ask it to give you a view on summarizing the JWST's groundbreaking observations of the early universe. And this is what it gives you. Well, it says here Webb's first deep field. That's not Webb's first deep field. That's actually not Webb's field, full stop. It's a completely fake picture, right? It has some beautiful lensing. So if this was true, that was like, oh, the whole new lensing system. But here is my advice to students: don't turn to AI. AI produces a lot of really bad things. And so this is not what is the overview of Webb. But what JWST really did is it brought us the redshift evolution, meaning what I'm showing here are the two graphs from a recent review paper on, if you look at the right-hand side, for example, the number of sources with spectroscopic redshift. This little green thing is what we knew from pre-JWST, and blue is already outdated version of what we know now. And we are really seeing a lot of new sources that we sort of thought they existed, but now we can really study them in detail. So that wasn't surprising. That was sort of expected. But what puzzles these observations brought are a couple-fold. So these are the ones that I'm going to focus on. There is, of course, a lot of other puzzles that are there. But one of the puzzles we are seeing is when we measure the UV luminosity function, we are seeing more galaxies than we expected we would see. And in particular, the blue and luminous ones are the ones that are kind of puzzling. I'm also going to talk about clumpy star formation and emergence of star clusters. It's amazing that with JWST, we can now see clusters, star clusters. I'm not allowed to call them globular clusters, but like star clusters in action, right? I'm going to be talking about little red dots and supermassive black holes. And I'm also going to be talking about very low metallicity galaxies. So to UV luminosity function, so this is a UV luminosity function at a redshift of 10. So what I'm plotting here is the number density as a function of absolute magnitude. And what you can see here is the luminosity function, but what is maybe even more exciting is the luminosity density, which is plotted here on the right as a function of redshift. And with these gray lines, what you have, the bottom gray line is what we had when we only had Hubble. So we thought that UV luminosity density is going to decline quite steeply. But when Webb came around, what we are seeing are, those are the gold points, is that there is a lot more UV luminosity density at higher redshift than we initially thought. So basically, however, what I'm going to be showing is that not all the points are giving you this high, this excess that we are talking about here. Because when we measure the luminosity function with James Webb, we can, of course, all of the measurements that we are making are with the imaging, right? We don't have enough spectroscopic power to really do the luminosity functions yet at those high redshift. And so this is a paper by a graduate student, now postdoc from the Canucks group, that looked at the UV luminosity function not with the standard broadband filters that everybody else was using, but rather what we use is all medium band filters and broadbands on board of NIRCam, and that's over 23 arc minutes squared. And so when we do the luminosity functions, again, this is just luminosity function at redshift between 9 and 12, and this is between 12 and 16. What our results are showing that these lines are slightly lower than the rest of the observations are showing. So one has to be careful, right? Because when you look at the measurements, those measurements are usually done in a single field, and there is a large cosmic variance between the fields. So maybe there are a couple of very luminous galaxies in one field, but that doesn't mean that the same is true in other fields. The other thing what you need to be very careful for is, of course, selection effect. And with medium bands, we have a much better handle on redshifts. And it seems like looking at luminosity functions, that there is still a considerable scatter. But looking at the luminosity density, it is true that even though we are not getting this is the luminosity density as a function of redshift, even though we are not getting as high of a values as some of the other fields, we are still getting, of course, more bright galaxies and more galaxies in general compared to what we were seeing from the HST. So what is this all telling us? Well, we're currently having sort of two puzzles here. So one is the one I already mentioned before, is the problem of blue monsters, that there are too many UV bright galaxies in the universe. So when we look at the tip of the iceberg, we are seeing a lot of UV bright galaxies, and so the question is, why is that? And there were a lot of answers that are proposed for why we are seeing so many bright galaxies, and they go from modifying the baryonic physics, meaning galaxies producing stars in a different way in the early universe, or compared to the models that we had before. There might be a different feedback. There might be dust being blown at large radii, so we can observe those galaxies more easily than we thought. There could be a top-heavy IMF, or there could be even a modification of lambda CDM. But before we claim any modifications of lambda CDM, what we really need to do is to exclude any possible contribution from A, B, C, or D, or even some other baryonic physics effect that we didn't even think about yet. So we do see a lot of bright galaxies, although the range is quite big. But really what I'm going to argue today is that we also need to look at the faint end, because obviously the bright galaxies are just the tip of the iceberg. If you really want to study reionization, if you really want to study the sources that are likely responsible for it, what you need is you need to look at the faint end. You need to look at the bottom part. And for that, we need gravitational lensing, because you cannot reach the faint end, which is MUV of fainter than -17, if we don't use the help of gravitational lensing. And of course, for that, you need to do lensing surveys. You need to stick a big galaxy cluster in front of your field, so that acts as a cosmic telescope, magnifies the background universe. Because really, what we think of is that the galaxies down to luminosity of 0.001 L star are contributing to reionization. It's mostly this faint population, although there is still some debate of who is really responsible for reionization. But if you look at here, what we are currently observing, so this is again the luminosity function as a function of MUV, we are only seeing galaxies down to 0.1 L star really, but what we really need to do is go all the way down to the 0.001 L star. And so for that, we need gravitational lensing. Because what does gravitational lensing do? So here's an image of Zwicky 18. And if you want to study galaxies like Zwicky 18 at redshift 8, what normal surveys would do, this is MUV of -14, and what you would see in even deep surveys is this. So nothing. There's nothing there. But if you put lensing by a factor of 40, this is admittedly a really large magnification factor, you are effectively increasing exposure time of your telescope by 1600 by mu square. So all of a sudden, what you are seeing is your galaxy comes into view. But now, in addition to that, not only are you increasing the exposure time, you're also increasing the resolution. And so your galaxy, oops, I apologize. So instead of having a galaxy like this, you're getting a galaxy like this, because your resolution is effectively improved with lensing. And so not only can we study galaxies in the early universe as big blobs, we can actually study their insides with very high details. So for that reason, we started the Canucks survey. It's the Canadian Nearest Unbiased Cluster Survey. We are imaging 5 clusters with a Webb for 200 hours, and we are using 3 instruments on it, not just Nearest, but also NIRCam and NIRSpec. And I'm going to show you a lot of results from Canucks today. If you're interested, Canucks had its data release on 30th of June, and basically all the reduced data is on the page. I highly recommend going to our webpage rather than to MAST webpage, because MAST has incredibly convoluted way of showing the data. I knew data that was there and I couldn't find it, so it's we have it a little bit more intuitive on how you can retrieve the data. But if you want, there are all the catalogs, all the lens models, everything that you might want is there, and you can see it for Nearest and NIRCam. But before I move on to show you Canucks results, let me start with a different cluster. So does anybody recognize this one? Anisha, you're not allowed to say anything. Anybody? It's a famous galaxy cluster. Does anybody know if I show you this image? Which cluster is this? Yeah? So this is Bullet Cluster. So we observed Bullet Cluster in cycle 3 with NIRCam and NIRSpec. And you can see this beautiful, I always, when I look at this image, it still sort of warms my heart. So allow me for a brief excursion of not talking about high redshift galaxies, but talking about Bullet Cluster. Because what we do with the Bullet Cluster, of course, we are going to be using it to measure the properties of dark matter. In order to do that, we need a precise lens model for this cluster. And what you see here is what the status of the observations was before JWST. So before JWST, we had 40 multiple images, 15 systems, and only 5 of those had spectroscopic redshifts. For those of you who don't do lensing, so what we are doing is we have background sources that are being multiply imaged because of the lens in the front. And these multiple images allow us to actually study the mass distribution of this cluster. The quality of the lens model depends upon how many systems you have and how many spectroscopic redshifts you have. So more is better, obviously. And so we can use this information to study the mass distribution in this cluster. And we have done this in the past, and we have measured the dark matter properties. This is the famous image, right? So this was the old times, but now with JWST, the situation is the following. So this is work done by my graduate student, Gregor Richtersic, who is amazing and applying for jobs. So if you have any jobs, please do let me or him know for a postdoc. And so he has been designing this data because he's also a PI on this proposal. And also he's going to be the main person measuring the dark matter properties and doing the lens modeling. Now we have 104 secure multiple images and 40 systems with spectroscopic redshift for this cluster. So we are getting much more detailed mass maps. And just for those of you who are not familiar, how we measure dark matter properties. So this is actually a merging cluster. So we had 2 clusters which in the past collided. Because clusters of galaxies also have gas in them. The gas slows down because of ram pressure stripping, and you can see the gas distribution sort of lining up in the middle between the two clusters. On the other hand, the galaxies from the two galaxy clusters, this is an old image, are effectively collisionless particles, and they travel through without the loss of speed. So they're coming right through. And then the big question was, what does dark matter do? If dark matter was collisional, it would end up more closer to the gas. If it's collisionless, it would end up lining up with galaxies. So with these new observations, we can measure this offset between dark matter and X-rays and the galaxies to less than 4 kiloparsecs, which is sort of shown here. So this yellow cross is the new resolution that we are getting. And this should, in principle, improve cross-section of dark matter particles, sigma over m. So cross-section of dark matter scattering per unit mass to less than 0.2 centimeters squared per gram. If there were any particle physicists in the audience, that's like a huge number. But remember, only astronomers have the access to really study dark matter cross-sections, because any particle collider works in a dark matter standard particle sector. And so they're studying different kinds of interactions. So that's really cool. Also, these kind of limits are interesting astrophysically, because if you want to explain some models of dark matter that were proposed to solve the missing satellite problems or too many satellite problem or too big to fail, then this would effectively rule those models out, because sort of sigma over m less than 0.1 centimeters squared per gram would not really make any observable signatures on, say, the amount of substructure we see around galaxies and the cusp core problem. Okay, so a little bit of an excursion. This is what we are currently getting. What really is why am I not giving you the sigma over m constraint yet is because now the hard work begins. We have measured what the distribution of total mass is. We have measured what the distribution of gas is. Now we need to run simulations to really see what that is telling us, because there is a lot of things that need to be checked. And for that, we are doing simulations. And once the simulations will be finished, then we'll be able to give you a good constraint. So stay tuned. OK. But now back to the high redshift universe. That was a short excursion into dark matter. But now, of course, the reason why we also secretly imaged this cluster is because I was also excited about high redshift galaxies. And here is one that we detected at redshift 11. So I'm calling it very imaginatively bullet arc Z11. We don't really have good names in astronomy, OK? So if you think there could be a better name, let me know. But this galaxy, you can see it here on the bottom. What we immediately saw is that it's not just a galaxy, but it has 3 unresolved or semi-resolved clumps in it. And what was also exciting about it, we put a slit on it with near spec. And so here is a spectrum of this galaxy. And we measure its redshift to be redshift 11. And even though there is a lot of lines here indicated, none of them is actually detected with a signal to noise of more than 3. So we're not yet seeing the lines, but what we are seeing is a strong damping of Lyman alpha, which indicates that there is neutral hydrogen in the IgM of that galaxy. Why am I so excited about that galaxy? It's twofold. One of them is if you look at MUV versus redshift plot for, I'm sure this is outdated by now, and I'm sorry, in the last 2 weeks I wasn't able to follow all the literature because we were doing proposals. But I can still, I think, say that this is the lowest luminosity redshift above 10 galaxy that we know of, so that's here. So we are really starting to spectroscopically observe galaxies at redshift, at luminosities of 0.1 L star or below. So this is exciting, but what is also exciting is that this galaxy is highly magnified. So my graduate student, Jon Judas, did the model, and so what you see here on the top is the observed image of the bullet arc, and when he models it as an extended galaxy and 3 clumps, two of them are small, one of them can be a little bit bigger, then he gets this model and relatively good residuals. So what we are seeing here is galaxy resolved at 10 parsec scale at redshift 11. And the nice thing about it is that we think is that this clumps 1, 2, 3 are probably, I'm again not going to call them globular clusters because these are not the same globular clusters as we know in our local universe, but they have the same properties as our globular clusters. They're very compact. They are very compact, and their surface density is very high. So we think they are in observations. They're very similar to the globular clusters we know in our Milky Way. So this is exciting because, you know, for the first time we can actually resolve 10 parsec scales in galaxies at those high redshifts, and we can really start to see the building blocks of these early galaxies. And this is obviously not the only example we have. Here is another one from a Canucks cluster. So this galaxy is called Firefly Sparkle Galaxy, or Christmas light galaxies, because this paper came out around Christmas, and of course everybody who saw that image of this galaxy was like, oh, Christmas lights. So maybe sometimes we do have good imagination of what to call things, but in any case, this particular galaxy is a galaxy which is a very low mass, and it has all these star clusters in them of masses between 2 to 6 times 10 to the 15 solar masses and sizes of less than 4 to 7 parsecs. The little sparkles have fractional mass of about 50%, and they basically are showing very interesting properties. So the nice thing is that this galaxy has a similar mass as the Milky Way progenitor would have at a comparable age. So it's like a really normal run-of-the-mill galaxy with little sparkles that we can see at redshift of 8.3. Why we tend to sort of call it globular clusters is because the properties, which is the surface mass density as a function of radius that I'm showing here, are sort of similar and a bit higher density than the globular clusters we see in the Milky Way, which are shown here with the crosses. If I put the bullet arc on top of that, it's sitting over there. So once again, very high surface density, very small things that we can observe in the very early universe. The big surprise for this one also came with a spectrum. Spectrum is showing us a lot of lines, which is great. But what we can measure from those, now the spectrum is only covering, so we have 2 slits here, so slit 1 and slit 2, and it's sort of covering multiple clusters at the same time, so there is no spatially resolved information here, although that is forthcoming. The observations will be done in probably 7 months from now. But what we can already see from those slit spectra is that when you measure the temperature, the effective temperature for those clusters is you're getting extremely high value. So the effective temperature is 10 to the 5 Kelvin, which is really difficult to obtain. The one way we think you could have such a high temperature is if you have a very top-heavy IMF. So take this with a grain of salt. I'm not claiming we discovered a top-heavy IMF. It's just that this data prefers top-heavy IMF over top light. Just so much. But once again, we are seeing star formation at incredibly low spatial scales, and I'm really excited about the IFU, the forthcoming IFU that we'll be getting of this object. So we are updating this plot. Basically, what gravitational lensing allows us is study objects down at 10 parsecs. In the field, even in the deepest survey, basically our redshift galaxies are more like blobs because the resolution that even NIRCam is giving us is sort of in a 100 parsec regime. But when you put lensing on top of this, you get a high resolution. You're taking your cosmic microscope to observe those galaxies. Then you can really see galaxies at finer and finer details. So here are some more examples. The sunrise arc, which has a lens star in the middle probably, or at least a couple of stars. Here's the firefly sparkle. Here is also cosmic gems at redshift 10. And now we can add another one here, which is the bullet arc, only 400 million years after the Big Bang, observing sub-10 parsec scale star formation. So that's so much about the cosmic microscopes. Now I'm going to move to a topic that I normally wouldn't be talking about because I probably know the least about. But on the other hand, this morning discussion really made me think that you might be enjoying that. So let me talk about black holes in the early universe. So here is an example that, that was published by Roberta Tripodi, who was my postdoc. And this is going to be published in Nature Communications. I mean, it just got accepted, so we're very happy about it. This is a little red dot, which are these enigmatic sources. Here you see an image of it. It's little, it's red, and it's a dot. So very imaginatively, we call them little red dots. What are they? So initially, they're just selected from data based on what we call the V-shaped spectrum, meaning they have a very blue UV part of the spectrum, so very blue optical slope, and a red, very blue UV slope and a red optical slope. So they have like a V-shaped type spectrum. What do they end up being? Well, at least some of them end up being AGN. And we know that because we see the signatures of AGN. In this particular case, we see broad and narrow H beta, but we also see higher ionization lines, N4 and C4. So the nature of them is still a bit debated, but I think what is going to end up at the end is they're sort of a combination of you know, maybe black holes and some star-forming galaxies on top of that. But in any case, these objects are turning out to be amazing because we can really study the formation of black holes in the early universe. When you go after this one and you measure its black hole mass, modulo all the complications that we might not exactly know how to measure black hole masses, but if you trust the measurements that everybody is doing, then this object have very massive black holes, especially in relation to its stellar mass. Once again, the stellar masses could be overestimated, because what we usually do is we take all the light that comes from that object and assign it an SED fit and measure the stellar mass. We try to model the AGN contribution, but we don't know how strong that is. So depending what you assume about the AGN, underlying AGN, your stellar mass can go down even by an order of magnitude. But in any case, even at the face value, what the problem with these galaxies is if you think about what's its black hole mass in this early universe, is the question of how do you make such a black hole with such a high mass this early on in the universe? So here are a couple of models. So here is the black hole mass evolution, I mean not evolution, but just black hole mass models as a function of redshift. This is our object in here, and so you can accrete at sub-Eddington at all times, and you won't reproduce this object. Or if you accrete at Eddington, then you would be you would be able to create such an object, but you would need seed mass of about 10 to the 5 solar masses. So it's pretty high, although today I was told not that high. Obviously, if you accrete at super Eddington, then your initial black hole mass can be much more manageable, but accreting at super Eddington at all times is problematic for the other reasons. So here we go. We have this black hole. It's very massive. We formed it. And we need to explain how it actually got here. Here is another one. So this one is behind the bullet cluster now. And this is at redshift 5.3. So, you know, we call this low redshift. Sometimes people laugh at me when I call redshift 5 low redshift. And for a good reason, right? When I started my PhD, we barely knew galaxies at redshift 5, and now we call those low redshift. But in any case, this is another enigmatic little red dot, because what we see in this particular one is the strong iron iron line, iron 2. We see O1, we see calcium triplet. And this particular one also had a first detection of the 1304 bump. So again, a lot of elements, chemically mature galaxies at redshift 5.3, and sort of the lines that we only are used to observing at low redshift for quasars. So that's exciting that we can now do this at high redshift. And the reason for this is because we do have lensing. So all these galaxies that I showed were lensed by a factor, this one by a factor of 2, bullet arc by a factor of 14, which once again increased our effective exposure time by a factor of this squared. So it's very, very good to be observing lensed galaxies. Okay, let me sort of finish by showing this particular galaxy. One of the main goals of JWST would be to find the enigmatic POP3 population, so the very early population of stars. And the POP3 would be characterized by the low metallicity, although that's by no means the only thing that you need to really say this is a POP3 population. So here is a Lyman alpha emitter. What I was the most shocked by this one is how strong the Lyman alpha. Remember, this is prism observations, which anyways dilute Lyman alpha already because of the spectral resolution, and yet we see this booming Lyman alpha from this galaxy. So this is a galaxy that's been that's at redshift 8.2. It's been magnified by a factor of 8, and we can see really nice Lyman alpha. But when we measure the gas phase metallicity of this galaxy, it's very low, by 1.4% solar. So at the time of publishing this, a couple of months ago, this was the most metal-poor galaxy known at redshift above 7. Now, this is no longer the case, right? Because even from this house, you have produced even more metal, you have observed even more metal-poor objects. But in any case, it's one of those where we see very low gas phase metallicity, and so we're wondering, what's going on with this galaxy. It's a very compact galaxy as well. It has a half-right radius of some 40 parsecs, so we're seeing this emission in very small galaxy. And once again, we would not be able to detect such a galaxy without gravitational lensing. So let me conclude today's presentation with some more general results that are coming from CONOX. Of course, individual sources are really nice. I really like this. You have one source and it's really cute, and you do all the analysis and you fall in love with it, and then you name it an ugly name. But anyways, what about population studies, right? When we really want to learn something about what early galaxies are doing, what you really need is also to do population studies. So here is one thing that we are also doing in CONOX is measuring the UV slope. What you see on the left is the literature values from Stark. On the right is my student Giordano Felicioni's work. So soon we'll be able to say something about UV beta slope of faint galaxies. Because of lensing, we can push down the MUV to minus 17 or 16 to measure UV slopes of these galaxies. We also do Xi-ion. So Anisha, before you stole her from me, has worked on Xi-ion. This is Xi-ion from a single field with CONOX, but we are doing this now for all the fields. So why measure Xi-ion? Of course, people working in these fields would know exactly why we want to measure Xi-ion. For those of you who might not be so excited about reionization and early galaxies, what is Xi-ion is the ionizing photon production efficiency, meaning how many ionizing photons a galaxy can produce. And you need those ionizing photons to ionize the universe. So we thought that in order to reionize the universe, what you need is this gray line. So this was sort of the canonic value pre-JWST, that you needed at least that many ionizing photons in order for galaxies with F-escape. Once again, those photons need to escape into the IGM as well for them to be able to ionize the universe. And what we are seeing now, so here are the measurements from us and also from the literature, is that the value is actually even above that. So we're good. We are producing ionizing photons in large quantity. The other thing that we also care about is dust. So some people might find it very boring, but I'm getting more and more excited about dust. And so what we measure is two things. We have measured the extinction curve. This is the work by Vlad and Markov. And we are extending this now also to lens galaxies, so we can go to lower masses again. So the extinction curve is now measured up to redshifts of 11, and we can see that the extinction curve itself flattens. Now the question is, why is that? It could be for many reasons. It can be change of the dust grain size distribution, maybe the change of the dust production sources. So basically, this is the first step for us to measure in order to then really tell what is going on in those early galaxies. Because when I started this work, everybody, and I started this work very early, right? I mean, I'm basically 20 years in this field. Everybody was of the opinion that at high redshift, you don't have any dust, right? above redshift of 6, you don't have to care about dust. Well, they couldn't be more wrong, right? Now we know there is dust at high redshift. We observe it, we measure it. And with Canucks, what we have also measured is the fraction of star formation that is obscured as a function of redshift. And you would think that if there was no dust above redshift 6, the fraction of obscured star formation would be 0. But it's not, right? And it's actually really high. At redshift 7 to 8, it's sort of 50%. It drops at redshift of 10, but there is significant amount of dust, and we are measuring it, and I think it's important in the whole story of what is happening in the early universe. So I'm in the end of my talk. I hope this wasn't like too much of a whirlwind of different results. If I got you completely lost, I would like to just, for you to remember this, that early universe is full of surprises. So it's becoming evident that the star formation as it's happening in the early universe is not what we think it is. So all the galaxies and black holes seem to be starting forming earlier than we initially thought, and differently, so the conditions are slightly different. And so there is a lot that we can study in the early universe in order to understand it. JWST itself has opened a whole new parameter space. Obviously, in terms of redshift, we all knew that it's going to break redshift barriers. It's breaking them maybe even as we speak, like every month or so you get a new redshift, sometimes even. It's breaking it in terms of luminosity as well. With gravitational lensing, we can study galaxies that have less than 0.1 of characteristic luminosity, even spectroscopically, which is great. And we can study galaxies at super high resolution. You know, we can resolve things at parsec, 10 parsec scales, even in a early universe. And all this information is giving us new interesting puzzles, right? Seems like globular clusters, or whatever you call those star clusters that are very compact and likely globular, are forming in the early universe. But they're very different than expected. One thing I didn't touch upon is they're expected also to be nitrogen rich, which is probably, we are seeing them being nitrogen rich, which is probably the consequence of them having really massive stars in them. There is dust in the early universe, and there are metals. Large amount of dust were unexpected, I should say, in early galaxies. Half of the star formation at redshift bigger than 7.5 is obscured, and near and dear to many of you in this audience is black hole formation. So black holes seem to be forming early, and they are very massive, which also gives us a new avenue to start to think about how they actually formed. And I'll stop here.